Welcome back everyone. In this video we will talk about linearization with the help of Taylor series. So the first order Taylor series approximation was f of x is f of x naught plus x minus x naught f prime x naught. We will take the help of this first order approximation to write down the linearized form of any function. So suppose I have a function that is f of x is equal to x square. So how to write the linearized form of this function is f of x, which is x square, that is f of x naught, that is x naught square plus x minus x naught square. No, this will be 2 times x naught. So this is the linearized form of this function f of x. Suppose f of x is root of x, then f of x is equal to root of x will become root of x naught plus x minus x naught root of x naught 1 upon 2 root of x naught. This is the derivative of root of x naught because f of root of x becomes 1 upon 2 root x naught. Similarly, if I have the function f of x is x to the power 4, then x to the power 4 will become x naught to the power 4 x minus x naught 4 x naught to the power cube. So let us see a practical example of this. So there is something called time constant. Suppose I have a ODE, that is dy over dx plus cy is f of x. So when we numerically solve this ODE, the delta t must be less than 0.1 time tau, or this condition may change depending upon the stiffness of ODE. So we'll not go into the details of this thing. We'll see that later, that how delta t is calculated, because there are other criteria also to get this delta t, so that my solution is stable, it is not diverging. So we'll not see that, but let us focus on this tau, because this tau is necessary to calculate this delta t. So tau is given as 1 by c. Suppose I am given an example. Suppose the ODE is dy over dx plus root of x is equal to 0. Now what will be the value of tau for this? Now since we see that this must be root of y. So since we can see that this is not linear form of y, so we cannot write down 1 by root c, because the constant is 1 but the power of y is not 1. So we need to get this power of y is equal to 1. So what we will do, we will write down the linearized form. So what will be the linearized form? Dy over dx plus root of y naught plus y minus y naught 1 upon 2 root of y naught, and then it becomes 0. So what I have? So I have that dy over dx plus root of y naught plus y upon 2 root of y naught minus root of y naught divided by 2 is equal to 0. So here the coefficient of y, that is c, is 1 upon 2 root y naught. So my tau will become 1 upon 2 root y naught, and that essentially becomes tau is equal to root 2 y naught. So here y naught, we can take the initial value of this y naught. So we will basically, while we are solving this equation, we will assume that y naught, and then we'll repeatedly solve this equation. So to calculate the time constant at each time step, we'll replace the value of y naught, and that will be the updated value. So we will see this how we can use this when we are trying to solve the ODEs. So this was about linearization, that how we can use the Taylor series approximations to find out the linearized form of any function. Thank you.